Hello everyone, my name is Boyan Chen. I'm currently a senior researcher from Huawei, Canada. In this video, I will present our paper towards training reproducible deep learning models. This is joint work between me and my colleagues and Professor Jaemin Jiang at York University. Currently, the domain of AI research faces reproducibility crisis. A paper published in Science in 2018 shows that among the surveyed 400 AI papers, only 6% includes code for papers' algorithms. None of the research methods, datasets, and experiment configurations are clearly documented for the surveyed papers. So currently it is very challenging to verify the research results, and this will further hinder the advancement of scientific research. Hence, in recent years, researchers from academia and industry practitioners work together to promote the concept of reproducibility. For example, in 2019, NeuralNIPS, which is one of the most prestigious AI conferences, has come up with a reproducibility checklist, which defines the concepts of reproducible. And as you can see in the bottom left corner, the AI model, if we consider it is reproducible, if under the same training setup, the resulting trained model yields the same results under the same evaluation criteria. On top of that, there are other concepts such as replicable, robust, and generalizable, but they're not the focus of this paper. There are generally three challenges of training reproducible deep learning models. And the first one is the software randomness, which could cause the results non-stable. If you look at the top two figures, there is a baseline to beat in the middle, and the results fluctuate a lot. If you pick the top three results, you will have a completely different interpretation when you compare with all the results. When you only look at the top three results, you will get the impression that the new proposed method is better, but it is not the case. The second figure shows that under different random seeds, how the results could fluctuate, and it even has a statistical difference. The second challenge is from the hardware non-determinism, and one of the issue is the rounding errors, which could accumulate to impact the results. In the GPU programming, as we know that especially in the CUDA programming model, it uses warps as units of computation. A warp usually consists of 32 parallel threads with concurrent memory access. And due to the limited precision of the deep learning models, the rounding errors are introduced at every step of floating point calculation. In the GPU model, concurrent accesses to a single memory address must be serialized to prevent race conditions with no guaranteed order of access. Take this as an example. Usually we know that A plus B and definitely equal to B plus A in most of the cases. But when different values come at different times, when you calculate A plus C first and then plus B, compare with B plus A first and compare C, then the results might be different. The third challenge is the lack of systematic guideline to instruct people to conduct the reproducible training process. Next, we're going to show you the current state of training reproducible deep learning models. And there are prior arts tackles these three problems, which is dealing with the software randomness, hardware non-determinism, and propose some guidelines. First of all, let's take a look at the software randomness. The most straightforward case is to set random seeds, like the top figure showed here. But the problem is setting random seeds is intrusive and usually very difficult to manage when the dependencies become more and more. At the same time, we have conducted informal surveys to practitioners, and we find out many of the cases they don't want to set a fixed seed to limit the exploration scope. So there is another way, which is to record the random state using APIs, and such API exists in frameworks such as NumPy and the Python internal random. All you need to do is first record the states when you invoke the random functions first, and then when you actually want to replay the state, you load the state object and conduct the process again. And as you see that these two results are will generate the same sequences. However, popular deep learning frameworks such as PyTorch and TensorFlow does not provide such features. The second part we're going to talk about is how do people right now deal with hardware non-determinism. And usually that's dealt with 3 ways. The first part is through the environment variables that provided by the frameworks such as TensorFlow here. You just need to set the environment TF deterministic ops, and it will try its best to select the operations that is deterministic. And also PyTorch provide API configurations that you can set in the training scripts. And there are also academic papers proposing new GPU architecture design, but it's still not mature. So the solution seems pretty scattered and no systematic evaluation. There are other approach to deal with the guideline issues we mentioned earlier, such as model cards and data sheet. But these are all in the documentation level, and we haven't found any automated process to validate. Here we present the overview of our approach towards training reproducible deep learning models. This approach consists of 5 steps. In the first step, we just conduct initial training using the original setup. And then we conduct the second time to check if the model is reproduced. If the model is reproduced, then we directly stop the process because everything is fine. If the model is not reproduced, then we profile and to locate the non-determinism introducing issues. After that, we update our strategies to deal with these non-determinisms. In the last step, we will conduct the record and replay process to record the random state so that we can replay the random state in the second try of the model training to further check whether the model is reproducible or not. During the process, we will for sure generate 2 sets of metrics, and one is the original one, the other one is the reproduced ones. Hence, there are the target models and reproduced models in the bottom. And the evaluation metrics are generally things like precision, recall, accuracy, F1 score, etc. And the process metrics meaning is about like the losses during the training. We will also generate a guideline and a random profile, which we will talk about later. So let's look at the record and replay mechanism for controlling the software randomness. In the profile process, we will locate the software randomness introducing system calls through a tool called strace. And this tool will give you a rough idea of what the functions can lead to the software randomness. In this picture, we will see that there are 2 major functions. One is getRandom. The other one is open the device devViewRandom to get the random numbers. To deal with this, on the right side, we conduct the record and replay process for recording the random state first and then replay it later. To do that, we use a mechanism called API hook, and that is a dynamic interception mechanism in the Linux operating system, so that we could actually intercept the system calls and add a wrapper on top of it. So let's say in the initial training, the getRandom function was called, and we add a wrapper, our own getRandom function, to record the random numbers returned by the glibc and put it in storage. We will do the similar things for the return values of the device dev_urandom and put it in storage. In the second process, which is the replay process, we will not invoke the actual getRandom anymore. Instead, we will directly retrieve the random numbers stored in the storage, so that we can use this to conduct the second training. In this way, we are able to control the software randomness. For the hardware randomness, we conducted a profile and patch method. First of all, we will need to use the tool called cprofile to get the low-level calls from the deep learning framework. And as you see here, we have a call bias add, which is exactly the causes the issue that I talked about before. The backdrop of bias add performs large structure reductions use the CUDA's atomic add. Therefore, it just captures the truly random alignment between the asynchronized compute engines and the randomly varying flow point rounding error in the gradient. To further understand whether we could cover all the non-determinism introducing functions, we refer to a open source projects created by NVIDIA. They have this open source non-determinism patch which listed all the currently known functions. And if the solution is available, it will show yes here, and we'll directly use the patch from NVIDIA. Here we present our case study setup for evaluation. First, we have selected 16 different experiment setups, which vary between hardware, software, whether it uses random seeds, whether it uses record and replay, and hardware patch. The setups are used to compare the variance between each factors, as we will see in the later presentation. For example, to check how the hardware non-determinism impact the results, we could compare the results between G2 and G4, where the random seeds are all controlled and set, but the patch is enabled and disabled respectively. For each setup, we ran the experiment 16 times, which are further divided by 8 pairs. The evaluation and process metric from each pair are compared to decide whether it is reproducible or not. For the models and datasets we use, we have selected 6 commonly studied computer vision related deep learning models, which are LeNet 145, ResNet 38, ResNet 56, WetResNet. The implementation of these models are adapted from a popular open source repositories. We have also selected the model X used in Huawei, which is a LSTM-based deep learning model used to forecast energy usage, and it is a regression model, different from the classification task the previous model doing. The evaluation results are presented in 3 dimensions: the process metrics, evaluation metrics, and the potential overhead. In the process metrics, we mainly show the losses of each epoch during the training process in 2 training with the same setup. As you can see, all the losses for each epoch are exactly the same. For the evaluation results, such as overall accuracy, per class accuracy, predictions, they are also exactly the same between each pair for the same setup. We're using our profile and patch plus the record and replay. As for the overhead, the generated random profile will take up a bit of storage costs, but it is not that much compared to the model size. As you see that ResNet 56 model size is 726.6 megabytes, where the random profile is only 13 kilobytes. However, on the other hand, for the time overhead, if we apply the hardware patch, it will slow down the training process. For example, when we were training the wet ResNet, originally it only takes 7.08 hours, but after enable the patch, it will take nearly 15 hours. It is understandable because the patch serializes certain parallel compilations to prevent rounding errors. But in summary, the takeaway of the evaluation results is, with our approach that control the randomness and control the hardware determinism, both process metrics and the evaluation metric can be fully reproduced. Here we discuss our variance analysis results, along with some interesting issues we encountered during the experiment. We evaluate the software variance while controlling the hardware variance, and vice versa. The original variance shows the results when none of the non-determinism are controlled. Let's take the ResNet 38 as the example. The largest variance of overall accuracy in the original setup is 2%, while the largest variance introduced by software randomness and hardware non-determinism are 1.4% and 1.2% respectively. For per class accuracy, the largest variance in the original setup is 10.1%, while the largest variance introduced by software randomness and hardware randomness is 6.8 and 4.9. And for predictions, we could also see the similar trend, while the original variance have the largest difference. So basically, the original variance are the largest, as it combines both software and hardware factors. And software variance are usually larger than hardware variance, although the hardware variance are not negligible. When conducting experiments on CPU, we find out that using different styles of import statements for chars in some versions might cause the results non-reproducible. The developers acknowledged the findings and asked us to use the newest versions to solve this issue. To get the details, please refer to our paper. But from this finding, we suggest that careful documentation is needed to specify dependencies and how they are used. And there should be rigorous ways to specify software dependencies, like software bills of materials. In summary, in this video, we first present that the domain of AI faces reproducibility crisis, and it is very challenging to do so. Then we present our approach, which is based on the record and replay for controlling randomness, and profile and patch for controlling the hardware non-determinism. We evaluate our approach on various CV models and one commercial model adopted currently in Huawei. The evaluation results show that both the process metrics and the evaluation metrics can be fully reproduced. Thank you, and that concludes my talk.